Hello, today we are going to discuss about a new topic, flexionality and NMR. What is flexionality or what is flexional behavior? Before that, we know that resonance is a delocalization of pi electron. Moreover, in resonance there is no change in the relative positions of atoms or group. Okay. And here this is, we know, this tautomerism, right? This is keto form, this is enol form. The basic difference between resonance and tautomerism is that in tautomerism we can see a relative change in the position of atom. See hydrogen here, but here hydrogen changed to this position. Delocalization present in both situations. Now we can see the next example, that is, this is, we know that N-dimethyl amide, that is DMF. Here we can see two methyl group at nitrogen. It is designated as MEA, it is MEB. At 100 degrees Celsius, what will happen is that it will undergo rapid rotation. That is, this bond can rotate, so you can have this structure. Now what happened is that this MEB relatively changed its position to MEA position and vice versa. This is nothing but flexional behavior. That is, molecule can undergo dynamic such that some or of their atom interchange between symmetry equivalent position. That is, it is the rapid change in between symmetry position, rapid interchange between symmetry position. That is nothing but flexionality. How can we detect this flexional behavior, whether a molecule showing flexional behavior or not? So the answer is that we can detect by making use of NMR. One of the extreme, NMR showing a particular peak, the same compound showing different kind of peak at another extreme temperature. That is, at low temperature there is no flexional behavior. At high temperature we can have flexional behavior. So see in this example, at 100 degrees Celsius, that is high temperature. High temperature, this molecule can undergo rapid change between MEA position and MEB, right? So it can occur this. So what will happen is that when we are analyzing this molecule by making use of NMR, NMR cannot distinguish between MEA and MEB. They cannot distinguish. That is, this rapid change happen beyond the NMR scale. So this NMR can have some time in order to detect the detecting molecule, but this rapid change happened before that. That's why NMR cannot detect this molecule. So the thing is that at high temperature the NMR can say these two ME are the same. That means this MEA, MEB treated as at the same chemical equivalent. They give you, this 6 proton give you 1 signal. But at low temperature, so that is, here it is room temperature. Sometimes you see it is minus degrees Celsius. So at room temperature, what will happen? There will some kind of tautomerism will happen. That's why some double bond here. So at room temperature we can detect these two. That is, there is no flexional behavior. That means these two Me group are at a different chemical environment. So this MEA give you one peak, this MEB give you another peak. So at room temperature, this N-dimethyl formamide DMF give you 2 peak for 2 methyl group. So that is the charm of NMR when we are relating flexionality. So briefly, so this N-dimethyl DMF at high temperature give you one peak corresponds to 2 methyl group. At a low temperature give you 2 NMR peak corresponds to 2 methyl group. Now we are discussing an important flexional behavior that is due to Berry pseudo rotation. Okay, what is basically Berry pseudo rotation? So it is mainly happen in trigonal bipyramidal molecule. So this is a well-known example, PF5. So in a trigonal bipyramidal molecule, what will happen is that there is a dynamic shift in the position of equatorial bond with the axial bond. So what will happen is that this is our trigonal bipyramidal molecule at a high temperature. At a high temperature, we know that this flexionality behavior happen at a high temperature only. At a high temperature, this axial bond distorted, this axial bond also distorted, so you will end up with this structure. Now it becomes square pyramidal structure. So square pyramidal structure in the sense is that these 4 bonds are in the corners of a square. Now it is in the axial position. Now it is square pyramidal structure. And finally, this F1 becomes this position, this F2 becomes this axial position. In effect, basically what happened is that axial F4 becomes equatorial position, that is F4, and here the equatorial F1 becomes axial F1. Here also axial F5 becomes equatorial F5, equatorial F2 becomes axial F2. So this kind of rapid exchange is known as Berry pseudo rotation. This is well known flexional behavior. Now how can we analyze this molecule by means of NMR? So what will happen at a high temperature, what will happen at a low temperature? For this molecule, the high temperature is treated at a room temperature and low temperature is minus 10 degrees Celsius. First we will move on to high temperature. We know that at a high temperature flexional behavior takes place, that is Berry pseudo rotation takes place. This axial and equatorial bond undergo this rapid exchange, that is all the 5 fluorine seems to be same chemical environment, that is all the 5 fluorine give you a one signal. So at a high temperature this PF5 molecule give you a single signal. Okay, what about lower temperature? At lower temperature we know that this molecule is rigid, there is no Berry pseudo rotation, that is there is no flexional behavior, So you can have 2 kind of fluorine, 2 fluorines are in the axial position, 3 fluorines are the equatorial position. So 2 axial fluorine give you one signal, 3 equatorial fluorine give you another signal. Okay, and we can have the splitting pattern also. So here I am not discussing splitting pattern. Okay, so here I discussed only the number of signal. Okay, so this another example, FeCO5 molecule give you this Berry pseudo rotation. So in this kind of trigonal bipyramidal molecule at a high temperature flexional behavior by means of Berry pseudo rotation takes place, and that give you only one signal. But at a low temperature it is rigid, that molecule give you 2 peak corresponds to 2 chemical environment, that is equatorial and axial. Now another kind of flexional behavior is due to ring whizzing process. For time being, this is the most popular organometallic complex showing flexional behavior. So this is iron 2 carbon compound, and here you have pentadienyl ligand. It's showing hapticity 5. Okay, and another cyclopentadienyl ligand that's showing hapticity 1. Okay, so the main interest in this complex is on cyclopentadienyl ligand having hapticity 1. So what will happen now? In this complex, it is bonded to, I marked it as 1, 2, 3, 4, 5. Now this ion is coordinated to this one carbon. Now it will undergo ring whizzing, means this ion is now bonded is into 1. Now it can bonded into 2, and it can bonded into 3, it can bonded to 4, it can bonded to 5. That means this ring can undergo some kind of dynamic change with respect to its position. Okay, dynamic change. So it is a flexional behavior. How it is happen? Now this pi bond can shift to 3,4 position. This pi bond can shift to 1,5 position. Now this ion is directly bonded to second carbon. So this situation. Basically, these are indistinguishable structure. Okay, they are chemically equivalent structure. That's why it is called flexional behavior. Again, here it can undergo this ring whizzing, that is flexional behavior. This pi bond can shift to 4, 5. This pi bond can shift to 1, 2 position. Okay, and this ion is directly bonded to third carbon. Now you can end up with this structure. So this is again chemically equivalent. So this way it can undergo flexional behavior. Now the interesting thing is that this flexional behavior can show at high temperature. Okay, at a low temperature there is no flexional behavior. Okay, so how a question comes in this situation? Now here you can have two ligand, that is a hapticity 5 ligand and a hapticity 1 ligand, eta 1 ligand. So the main focus on this hapticity 1 ligand, that is eta 1 cyclopentadienyl that is directly bonded to metal. So I am taking this as a situation. This is generally metal. Now this is your ligand. Now basically when we are analyzing, here you can have one proton, here you can have one proton, here you can proton. This proton is one of the chemical equivalent position, that is designated as HA, and these two proton, they are in the same chemical environment, that is designated as HB, and these two are in the same chemical environment, it is designated as HC. Now at higher temperature we know that ring whizzing takes place. This M can occur this position, that is all the hydrogens are the same at high temperature due to flexional behavior. So all these 5 hydrogen give you a single peak at high temperature due to this flexional behavior at a high temperature. That is at a high temperature give you only one signal, says 30 degrees Celsius, one signal. But at lower temperature there is no flexional behavior, so NMR can distinguish these two hydrogen. At low temperature, that is minus 80 degree, you can have one signal corresponds to this hydrogen, one signal corresponds to these two hydrogen, one signal corresponds to these two hydrogen, that is 3 signal. Okay, this is very important. Okay, ready. So here we can discuss a problem. The question is that how many signals in proton NMR for a organometallic complex MnCO thrice eta 3 C3H5 at minus 70 degrees Celsius. So the given complex is nothing but this one. Okay, this is a allyl ligand having hapticity 3. Okay, that is it is ligated via this 3 carbon atom. Okay. Now this is this ligand is our interest. Okay, so So the question is that minus 70 degrees Celsius, clearly it is low temperature limit at lower temperature. So in general we know that at a high temperature limit, that is at a high temperature, you can have flexional behavior. At a low temperature limit you cannot have flexional behavior. So here you were asked at a low temperature limit, that is the NMR regarded with there is any kind of flexional behavior. So first we can simply check at high temperature. So at high temperature what happens is that at high temperature you can have a rapid exchange between the that is a rapid exchange of the position of a Mn. So initially you can have Mn here, and it can, that is hapticity 1, it can have hapticity 1, then hapticity 3, and this end it can have this end hapticity 1. That means there is a rapid exchange between this terminal to this terminal at a high temperature. That is nothing but, here it is flexional behavior. That means at a high temperature these two hydrogen and these two hydrogen, they are in the same chemical environment. That is, in effect these 4 hydrogen are equivalent, and this is entirely different. So at high temperature, due to flexional behavior, it can have two kind of chemical environment. That is, it can exhibit 2 peak in NMR due to this 4 and this single hydrogen. That is, it can show 2 signal having 4:1 ratio. But at low temperature limit, at low temperature there is no flexional behavior. So this is the situation. You can have HA, HB, HB. Why this HA, this HB? The thing is that these HAs are seen with respect to HC. That means they are in the same side. And this HBs are anti with respect to C. So at low temperature this is rigid. There is no dynamic. Okay, it is static. So that's why these HBs are different. So that is, it is anti with respect to HC. HAs are seen with respect to HC. That's why you can have 3 chemical environment. That means you can have 3 signals corresponds to 2:2:1 integration ratio. Okay, so it is very important problem. This kind of question may ask. So another interesting organometallic complex showing flexional behavior is this complex. So here 2 CP, that is cyclopentadienyl ligands, are having hapticity 5 and 2 having hapticity 1. So here the flexional behavior is that these 2 ligand can interchange. That is, it can change from hapticity 1 to hapticity 5. Hapticity 1 to hapticity 5. That is one mode of flexional behavior. Another mode of flexional behavior we have discussed earlier, that is ring whizzing. That is, this hapticity 1 ligand can undergo ring whizzing, and this titanium can bond with all these 5 carbon atom in hapticity 1 cyclopentadienyl compound. That is one flexional behavior. Another flexional behavior, this can undergo rapid change from eta 5 to eta 1. Okay, so this particular organometallic complex can showing these 2 kind of flexional behavior, 2 flexional behavior. So how can we detect this flexional behavior? The same way we can detect by means of NMR. So in general, at low temperature, that is minus degree Celsius, there is no flexional behavior. So we can distinguish the hydrogen present in the ligand. Okay, but at high temperature, that is at high temperature it is 62 degrees Celsius. At a high temperature 62 degrees Celsius, what will happen is that 2 kind of flexional behavior takes place. That is ring exchange as well as ring whizzing takes place. So that means we can have 5 hydrogen in eta 5 hydrogen in eta 5, that is 10 hydrogen. So this 10 hydrogen as well as 10 hydrogen from here. So in effect all the 20 hydrogens are in the same chemical environment at a high temperature, that is 62 degrees Celsius. That is all the 20 proton give you a single peak. So that is due to only flexional, the flexional behavior. Okay, due to only the flexional behavior. Interestingly, in this molecule at minus 30 degrees Celsius, it is not lower temperature limit, it is intermediate temperature limit. At minus 30 degrees Celsius for this complex, there is no ring exchange flexionality. But there is only one kind of flexionality, that is this ring weaving takes place. So at minus 30 degrees Celsius, five plus 5, that is 10 hydrogen from eta 5 ligand give you a single peak, that is 10 hydrogen from eta 5 cyclopentadienyl give you one peak, and 10 hydrogen from 2 CP group, that is eta 1 CP group, give you one peak. So I repeat, at minus 30 degrees Celsius, that is intermediate lower temperature, there is only one kind of flexional behavior, that is there is no complete flexional behavior, that is there is no ring exchange. So we at this temperature we can distinguish eta 1 CP and eta 5 CP, that is eta 1 CP proton, that is 10 proton from eta 1 give you one peak, and 10 proton from eta 5 give you another peak. Okay, ready. At minus 80 degrees Celsius, strictly we can say that there is no flexional behavior, So in the case of eta 1 CP, as we mentioned earlier, you can distinguish all the proton present in the eta 1 CP, that is this is bonded to metal, and this is one kind of HA proton, these two proton and another proton, these HC protons are another proton. So this eta 1 CP give you 3 peak at minus 80 degrees Celsius, that is lower limit temperature. So clearly there is no flexional behavior. Ready? So that is the case of this complex. We move on to another problem. So question is that find out the number of peak in 19 fluorine NMR as well as in 31 phosphorus NMR at a high temperature as well as lower temperature for a molecule, that is F3PPH2. Okay, so the structure of molecule is given by this. It is diagonal pyramidal structure. So according to Benn rule, these two fluorine occur axial position. So Benn rule says that most electronegative element occur axial position. Okay, axial position having less S character. Okay, so this is the structure. So we already mentioned that trigonal bipyramidal molecule can undergo flexional behavior due to Barry pseudo rotation. So it will undergo flexional behavior, okay, at lower temperature. So first of all we move on to lower temperature condition. At lower temperature, when we are taking 19 fluorine NMR, so what we will do, first evaluate how many fluorines are there. At low temperature we know that no flexional behavior, that is this molecule is rigid. So you can have 2 axial fluorine, 1 equatorial fluorine. That means you can have 2 peak in fluorine NMR, 2 peak. Okay, so how will be the splitting pattern, that also we can check. So 2 fluorine, this 2 fluorine give you splitting, that is we can check this fluorine, that is this 2 fluorine, axial fluorine. So this is our compound pH, F. Okay, so here we are analyzing axial fluorine. So 2 axial fluorine. First of all, this axial fluorine coupled with this phosphorus. This phosphorus also NMR active, that is phosphorus 31. Okay, so that is first coupling takes place. So we know that it is only 1. So according to our equation 2Ni plus 1, that is our hyperfine splitting. How many lines are there? So we can calculate the lines by making use of this equation 2Ni plus 1. So 2N, 1 phosphorus, I for phosphorus is half. So that is equal to 2 into 1 into half plus 1, that is give you 2. Okay, 2. That's why it is splitted into 2, doublet. Okay. Now next, this 2 fluorine, okay, it is coupled with this equatorial fluorine. This equatorial fluorine, that is JFF, that is fluorine coupling. So how many fluorine? Only 1 fluorine. That fluorine having I value half, that is 2Ni plus 1. It is, we can reduce it to, if a complex having, or if an atom having I is equal to half, then we can simplify this equation Ni 2Ni plus 1 into N plus 1. Okay, N plus 1. So here we can have only 1, so N plus 1, 2. So by means of this equatorial fluorine, it will split into 2. Okay, that is 2. Okay, so this axial fluorine showing 1 peak that split into this fashion, that is doublet of doublet. First of all split into doublet, then again split into doublet, that is called doublet of doublet. Okay, this splitting pattern like this, doublet of doublet. Ready? Now that is, you can have 2 into 2, first split into 2, then again split into 2, that is first splitting due to phosphorus 2, again splitting due to fluorine 2. So totally you can have 4 lines, that is doublet of doublet. Now what about fluorine equatorial? Equatorial we can analyze. This is our fluorine equatorial. So here we can have 1 fluorine equatorial. First, this fluorine equatorial is coupled with this phosphorus. So as we mentioned earlier, phosphorus having I value half, then N plus 1. So it will split into 2. Okay, so JPF split into 2, right? Now it will coupled with 2 axial fluorine. So 2 means N plus 1 give you 3. So that is each peak split into 3. That means you can have doublet of triplet. First split into doublet, then again split into triplet. That means it is doublet of triplet. Okay, totally you can have 6 lines. That is F equatorial. First it split into 2 due to phosphorus coupling. Again it is split into 3 due to fluorine coupling, axial fluorine coupling. Totally you can have 6 lines, that is doublet of triplet. Okay, so this splitting pattern I can explain by using a general. If you have any doubt, I can explain. So this is our organic compound having 3 different proton environment. So one is HA environment, other one is HB environment, other one is HC environment. Okay, that means this organic compound give you 3 different peak. First of all, we can have the peak, we can analyze the peak of HA. Okay, so HA peak. So we can have coupling. Okay, so here we can have coupling due to HB, here we can have coupling due to HC. Okay, so we know that distance, bond distance increases, coupling also decreases. So clearly first HA coupled with HB, okay, that is JAB. That is due to the presence of one proton, its signal split into 2, that is in accordance with the n plus 1, that is 2ni plus, we know that 2ni plus 1. Here for proton I having half value, so it is reduced to n plus 1. Okay, so we can have only one proton, so HA split into 2, right? Now this HA coupled with HC, so we can have 2 HC, so 2 will split into 3, that is this each peak split into 3. Okay, 3. That's why it is doublet of triplet. First it is split into 2, then again split into 3. That is called a doublet of triplet. Ready. Now we can analyze the peak of HB. Right. First this HB coupled with HC, so its peak is split into 3 due to 2 HC. Okay, 3. Okay. Then HB is coupled with HA, that is each peak split into 2 due to HA coupling of B with C. Okay, each split into 2. That give you triplet of doublet. First it is split into triplet, then it is split into doublet. That's why it is called triplet of doublet. Okay, so the concept is clear. Now we move on to phosphorus NMR for the same molecule. So for that phosphorus NMR, we want to analyze how many chemical environment are there. We know that one phosphorus chemical environment, that's give you only one peak. Now the splitting pattern, we know that at a lower temperature it is rigid, so you can have two different chemically distinct fluorines, that is axial and equatorial. So first it is coupled with this axial, that is 2 into half plus 1 into this one equatorial, 2 into 1 into half plus 1, that is 3 into 2, 6. That means first it is split into 3, then it is split into 2, that give you triplet of doublet. Now at a high temperature, what will happen? We know that at high temperature flexional behavior occur. That means due to the rapid change, that is exchange between this axial and equatorial, these three fluorines are the same. Now in the fluorine NMR, all the fluorines are the same chemical environment, and you can have only one signal. That signal it split into doublet due to the presence of one phosphorus, that is 2 into n half I for phosphorus, 2 into n is 1, I for phosphorus half plus 1, that is give you 2, so doublet. Ready. Now phosphorus NMR, you can have one phosphorus, you can have 3 chemically same fluorine, so that is 3 chemically same fluorine. So according to the equation, 2 into 3 into half plus 1, that is give you 4, that is single signal split into 4, that is quartet. Okay, clear? Okay, thank you. So if you are thinking it is important, please like and share. Take care.